Today we're going to explore a fundamental topic in solid-state chemistry, crystal defects and their types. While crystals are often imagined as perfect arrangements of atoms, in reality, they contain imperfections, and these defects actually play a crucial role in determining many of the physical properties of materials. Crystals are made up of atoms arranged in a very orderly pattern. However, in the real world, no crystal is ever perfect. There are always some irregularities or disruptions in the structure, and these are what we call crystal defects. These defects aren't just flaws. They significantly influence how materials conduct electricity, respond to mechanical stress, or interact with light. Crystal defects are classified based on their dimensional impact in the lattice. We have point defects, which are limited to a single atom or a lattice point, line defects, which involve rows of atoms, and surface defects, which affect larger two-dimensional areas like grain boundaries. Each type plays a different role in the properties of the material. Point defects occur at or around a single atom position. There are three major types. A vacancy defect happens when an atom is missing from its place. In an interstitial defect, an extra atom is crammed into the space between regular atoms. And in a substitutional defect, a different kind of atom takes the place of a regular one. These tiny imperfections can influence conductivity and diffusion. Now, let's take a closer look at two special types of point defects found in ionic compounds. A Schottky defect occurs when equal numbers of positive and negative ions are missing from a lattice, maintaining overall charge neutrality. A Frenkel defect happens when a cation leaves its position and moves to an interstitial site. Line defects, or dislocations, are one-dimensional defects. An edge dislocation is like inserting an extra half-plane of atoms into the crystal. It causes stress and distortion. A screw dislocation is more like twisting the crystal structure, causing a spiral arrangement. These defects are crucial in understanding how metals deform under stress, which is why they're studied extensively in materials science. Surface defects occur where different regions of the crystal meet. Grain boundaries, twin boundaries, and stacking faults are common examples. These defects can hinder or promote the movement of atoms and affect mechanical strength and corrosion resistance. That's why refining grain size, for instance, is an important way to make metal stronger. To wrap up, no crystal is ever completely perfect. Defects are a natural and often useful part of a material structure. We've covered point, line, and surface defects, each affecting material properties in unique ways. Understanding these imperfections is essential in chemistry, especially when designing materials for electronics, construction, and advanced technologies.